So, welcome to GeNoCAS. Our talk today is the title you can see there, K-theory equivariant sheaves, and the speaker is Guido Arnone. Please, Guido, go ahead.
Okay, thank you, Willie. So as you said, I will be speaking about K-theory of equivariant sheaves. This is some joint work with Devarshi Mukherjee, who's in the audience, and with Thomas Nikolaus. And I guess perhaps what I should do first is describe somewhat the things in the title. So let's first speak about the setup. For today, I'll be considering locally compact Hausdorff spaces and sheaves on them with some coefficients. And the coefficients will be on some dualizable category. You can safely think spectra or the right category of some ring. And very importantly, also perhaps K-theory, which will play a role later on. And our main object of interest will be related at least to sheaves on X. The equivariant part will come in a second. So this is sheaves on X with values on C. Right, and promptly we will consider an action in X, which will produce an action in this category. But for the moment, I want to say what K-theory will mean for me. So K-theory will be Efimov's K-theory. Now, let me briefly tell you what this is. So first of all, I should speak about the domain of this functor. This is a functor of this form, where the domain is the category of dualizable categories. So I haven't really given you the definition of dualizable categories, but you can think of these examples for now. And functors between them will be morphisms satisfying some condition, which is that they're strongly continuous. That means they're left adjoint, and the right adjoint is also a left adjoint. So the two examples that I want to concentrate on are, for example, if you have a proper map between locally compact Hausdorff spaces, then you have a pullback functor between sheaves. And here, when I don't put coefficients, I mean some dualizable category, this will be strongly continuous, for example. Or if I have an open inclusion, then pull back along this, say it's called I. It's a left adjoint, but it is also a right adjoint. So we also have a strongly continuous functor. And this is covariant. Okay, so for example, these two things are strongly continuous functors. And I should also say if C is dualizable, sheaves on X is dualizable. So these kind of things live in the domain of K-theory, and all I will need about K-theory is that it's a functor from Cat2 to spectra, and it's a localizing invariant, meaning it maps cofiber sequences in Cat2 to cofiber sequences of spectra, and it's compatible with filtered colimits. And it's the universal such thing, and that will be enough for our purposes. And one last thing, so in the talk today, we'll be interested in finite groups acting on spaces and equivariant sheaves. And that means just fixed points. So if X has an action by G, then you can produce an action on sheaves. And there's an abstract definition you can give for fixed points generally. It just takes some limit over the G-shaped diagram. Okay. So far, are we okay with this? Okay, so perhaps the motivating question for our work comes from some theorem of Efimov, which answers the question, what is the K-theory of the category of sheaves on X? And how is it related to the topology of X itself? And the theorem says this is precisely controlled by sheaf cohomology, concretely compactly supported sheaf cohomology on X, with coefficients on the K-theory of whatever dualizable category of coefficients we took in the first place. So we take K of C, this is a spectrum. Now we take the constant sheaf with those values, and then we consider compactly supported cohomology items. So this is precisely the K-theory of sheaves on X. Okay, so the goal today will be to understand analogs of such a result for equivariant sheaves. And also, and to emphasize some
You want to
analogy.
say what the analog of Efimov's result is for continuous functions?
Yes, I was about to say this. Like in some analogy, we will also say something about cross products of continuous functions over a space with an action of with G. Of course, G acting on X on the first place. And yeah, thanks for the comment. So this is also to emphasize that one can think of this as some sort of analog of continuous functions on X. In fact, a very similar argument one can do to produce the result here shows that, for example, if you do K-theory of C of X, you can also describe it in terms of compactly supported sheaf cohomology, and now K-theory of the point. So we'll have similar results for equivariant sheets on X and also for cross products of continuous functions. And here we will talk about topological K-theory, but we will also determine this as an object in E-theory. Right. Okay. To do this, we'll do a detour, and to motivate this detour, why we will concentrate on what we will ultimately, I want to first give you a sense of how you can prove this theorem by Efimov and which ideas come up that we will then later extend. So let me give you a sketch of the proof of Efimov's theorem, or one way one can prove it. Right, so the idea is you fix X and consider a sheaf on it. And ideally, you would want this to be on each U. You take K-theory of sheaves on U. But at least with the words that I've said until now, I haven't told you how to make this into a functor contravariantly on opens. But we do know it's a contravariant functor on compacts, because proper maps give you strongly continuous functors. So what you can do is you can build a sheaf, which in each U takes this limit of compacts inside U, and K-theory of sheaves on, and this compact should be named L, because there are too many Ks otherwise. So one shows that this is a sheaf. And then from all the maps from L to the point, one can actually produce a map between the constant sheaf the constant sheaf with values kc. Here C is playing the role of sheaves on the point. To this f of x. And one can check that this is a stockwise equivalence. So basically, if you compute the stocks on the right-hand side, you're again evaluating on sheaves on the point, and this is also K of C. And so if we were working with one category, we would be basically done. This would tell you this is an equivalence, but for infinity categories, this is not enough to have an equivalence. We need X to be nice of some sorts, by which I mean hypercomplete, but for example, if it's a CW complex, this would be enough. And so the trick, so to speak, or some solution to this problem is to use that if X is locally compact Hausdorff, say, then you can embed it into some Hilbert cube by Urison's theorem. Now the cube is now a limit of finite cubes. And since K-theory of sheaves is compatible with such cofiltered limits, then you can reduce to finite cubes. And there the space is nice enough and you can produce the same argument that I just outlined, but you do get an equivalence. So I just say this to emphasize like 3 points. There'll be a relation between compacts and opens. There'll be some argument which depends on stocks. And also the cofiltered limits of compact spaces play a distinguished role because they're, for example, important in this argument to get rid of some technical issues. And so what we will instead do before like tackling the question of the K-theory of equivariant sheaves, immediately we will first delve some time into functors out of the category of locally compact Hausdorff spaces with an action of G that satisfies some sort of nice descent conditions. So for example, they map cofiltered limits to filtered co-limits, their sheaves with respect to open inclusions, and so on. And thereafter, we will try to adapt these arguments to give a general statement on such functors, and this will imply something about K-theory. All right.
Yanu raised his hand.
Please go ahead then. Okay, so there's a question, sheaves on U is always contravariant in U here. For the time being, yes. I will speak about the functorality issue in a second, but out of the words that I just said, yes, and that's only because the only strongly continuous functors that I considered so far come from open inclusions and proper maps. So, so the other way around. Like this is covariant in U and contravariant on compacts. But we will deal with this point later. This is just a matter of the exposition I just did. I don't know if this answers your question, but you're covariant in opens for now. In particular, that's why you don't define this to be K-theory of sheaves on U. That would not even, with the words I said at least, would not even have the right functorality. Like the direction of the arrows wouldn't give you a sheaf. It is a co-sheaf, but I don't want to get into that. Okay, so this was to say then our first point would be to analyze functors satisfying some type of descent. And we will consider 3 categories as our domain. One is locally compact Hausdorff spaces with an action of G. The other one is compact Hausdorff spaces with an action of G. And then there's a further category that we will consider, which is partially defined proper maps between locally compact Hausdorff spaces. And that means the spaces will be locally compact Hausdorff, but a map will be given by a span, which is first given by an open inclusion and then given by a proper map. Now, a quick motivation as to why one would want to do this is that this, for example, would give you the correct functoriality for sheaves on X if you want all the functors to be strongly continuous. Because then you would have the upper star gives you a functor from sheaves on Y to sheaves on U, and then you can covariantly go to sheaves on X. Right. So at the very least, from the things that we've seen so far, it would make sense to consider such a span category. And the PDP here is just to say that these are partially defined proper maps. Okay. So descent conditions. If you now have a functor contravariant from locally compact Hausdorff spaces with an action of G, then we will care about mostly 4 conditions one can impose. One is open descent, meaning if you restrict F to equivariant opens of a certain X, which can be identified with opens of the quotient, then all of these are sheaves. Okay, you can also say this as F being a sheaf in a big site of locally compact Hausdorff spaces, but it turns out to be the same. So that would be open descent. The other condition that we'll care about is closed descent. And this is kind of related to open descent, but only for pullbacks. So this means every time a space is a union of 2 closed spaces, then you have a pullback, where you have the union, the factors, and the intersection. And the third condition is what we call cofiltered compact codescent, which admittedly is kind of a mouthful. So I'll just say CC codescent. And that means that if you have a cofilter limit, like our Q situation here, of compacts, then you map it to a filtered colimit.
Sorry, question. When you say in CHG, do you mean that the limit is also there?
Yes, but that's always true, I think.
Yeah.
Because,
The
I mean, products of compacts are compacts, and
always compact. Okay.
yeah, I mean, everything is Hausdorff here, so you're close to a product of compacts, then you're a compact. Well, actually, I mean, what I just said is actually always true. What I'm saying is that the limit is a closed subspace of a product that perhaps needs Hausdorff, but we're fine. Yeah, you can also express this as it's a limit in LCH, but you want all of the factors to be compact. Okay. Okay. Now, 2 and 3 you can also define for functors coming out of compact Hausdorff spaces. For 1, you need to speak about open inclusions, so you want to be in LCH. And there's a further thing you can consider if your functor is defined on this span category, which is what we call open-closed excision. And it goes as follows. So if you look at the shape of the spans and choose one of the 2 arrows to be identities, Then for each open inclusion, you get a covariant, a contravariant functor from LCH with open maps to this span category. And for each proper map, you'll get a map which is covariant. So you get an embedding of locally complex Hausdorff spaces with proper maps into this category. So in particular, every time you have an open set inside X, then you can always produce a map in this span category from X to U and from the complement to X. And we say F satisfies open-close excision if this gets mapped to a cofiber sequence. All right. I should say if there's any functor at all satisfying this, else that'll be sad. And of course there is. So, for example, if we view K-theory of sheaves, something, say, in compact Hausdorff spaces, then this satisfies 2 and 3. It has closed descent and it has cofiltered compact codescent. And pushing this analogy, sorry, I missed a G here. You can also say the same, for example, for continuous functions crossed with G. I mean, this one perhaps is not obvious, but let me just say that it is true. For the right-hand side, well,
You want to put a K top to land in space.
you want to put a K top, yes. Thanks.
Is it C or C0?
Yeah, it's
It's C just because I chose compacts.
Because, yeah, compacts, but yeah, even above it was C0.
It says F goes from LCHG.
Yes, what I'm saying is like for the first three.
No, in 4. F
in 4.
Yeah, you're
domain
you're-
Let me clarify this. Yes, I got the question. So if you have a functor out of LCH, you can ask whether it satisfies 1, 2, or 3. If it's out of CH, you can make sense of what it means to satisfy 2 or 3. And if it's out of LCH with partially defined proper maps, then you have CH embedded into it. So you can ask whether it satisfies 2, 3, or 4. Okay, in my example, my functors go out of CH. And what I'm saying is that they satisfy properties 2 and 3. I didn't say anything about 4 yet.
But you asked for property 4 in the case when X is locally compact, not just compact.
Yes, and I'm saying the example I just gave does not fit 4 yet. But we will produce out of this functor, which has domain CH of G, we will produce a functor on LCH of G partially defined in a couple of results from now. But for the time being, I'm only saying that these functors defined in compact Hausdorff spaces with an action of G satisfy properties 2 and 3. I'm not saying anything about 1 or 4. Is that okay?
But the example is only on CHG. Okay.
Yeah, and maybe for some peace of mind, again, this one requires some work, but for the right-hand side, this is basically the point that Gelf and Neimark gives you an anti-equivalence between spaces and C-star algebras. And so, in particular, limits go to co-limits. So it makes sense that co-filter limits go to filtered co-limits. Then you have to do some work to show that if you cross with G, everything is fine. And if you take topological K-theory, that too. But just to give you a sense, that should be morally what's going on. Okay. So perhaps exactly to answer your point, the idea will be that if you impose these descent conditions in various ways in these three categories, then once you impose the conditions, having a functor on any of them turns out to be the same. So if you have a functor on LCH with some descent conditions, this will uniquely determine a functor on CH with some descent conditions, and with LCH on proper partially defined maps with some descent conditions. So let me just state the theorem. Okay, so for example, you can take functors out of locally compact Hausdorff spaces, and you can ask them to have open descent and cofiltered compact codescent. This is the same as to have functors out of compact Hausdorff spaces with closed descent and compact cofiltered codescent. And this is also the same as to have functors out of the partially defined maps category, where you have open closed excision and cofiltered compact codescent. So once you impose descent conditions, all of these things will be basically the same. And I can tell you a bit about why. So, right.
So in the last one, you have this span category, right?
Oh, yes, thanks. I missed that. Yeah, that's partially defined proper. Thank you. Yeah, okay. So on some of the directions, the maps are relatively straightforward. You can embed CH into LCH, and you can also embed CH into the span category. Just you put identities and then proper maps. So on those directions, you just take restriction along those inclusions. The point is what to do in the inverse direction. And so let me just tell you what to do. If you have a functor on compact Hausdorff spaces, then what you do is you write can extend. Which will produce some functor on locally compact Hausdorff spaces out of abstract nonsense. All of the work is to show that this actually satisfies the descent conditions that you want. And this boils down to a result by Lurie, which is the equivalence between sheaves and K-sheaves. So let me not get into that right now. And then for the other equivalence, this is also something that has an analog for C-star algebras, for example, like when you define C0 out of Cx, which is if you now have a functor only on compact Hausdorff spaces and you want to build a functor on the whole span category, that at least on objects, what you can do is you can one point compactify, and then the inclusion of this point gives you a map like this, and you can take fiber. And then you check that this has all of the descent conditions and they have mutual equivalences. So of course this takes work, but I just want to state what holds. Okay, so all of these are the same picture, so to speak. In particular, this functor was only defined on compact Hausdorff spaces as I defined it, but it will canonically define something on partially defined maps. And in fact, if one checks, this gives exactly this functoriality that I was talking about, where you take upper streak of open inclusions and upper star of proper maps. Okay, and then another thing that we have is that for all of these categories, but let me state it for one of them, if you further restrict to orbits, so the spaces of the form G mod H, then this is conservative. So basically, if you have two such functors satisfying descent and a comparison map between them, then you can check whether this is an equivalence by checking on orbits. And It is my hope that this rings a bell when you compare it to this argument of Efimov's theorem. You have like two sheaves, and you check that something is a stockwise equivalence, and then with some trick you can push this into an equivalence. So the proof is inspired in this kind of arguments, but the sheaves are now for a fixed x. You build some sheaves on its orbit space, and that is why points or stocks of such a sheaf are corresponding to orbits, right? Which are points of the coarse moduli space, of the quotient space.
So for 2, do you strongly use that G is finite? Could you
That's
do
a good
without
question.
finiteness?
I think so, and I mean, okay, let me just give you I'll say a quick comment. So if you have a finite group acting on X, then it is true that equivariant compacts of X are the same as compacts in the quotient space. Right. I mean, if you have an equivariant compact, you push, you get a compact. If you pull back, you get a finite union of compacts.
It's not the best letter to choose.
That is absolutely true.
You might write com with a K if you are aware. If you woke up German today.
Okay, let me state it like this then. So for infinite groups, that's not true. I'm not saying one can't fix this, but we want to use some sort of correspondence between compacts and opens. And we want to use that both things are identified with compacts and opens in the quotient space. For opens, this is always fine because an equivariant open is the same as an open in the quotient space, but for compacts, this is not true, right? So at least if G is finite, then you're fine. Sorry?
And I guess the quotient space itself is problematic if G is infinite, right? It's like a non-Hausdorff horrible space.
Yeah, that is also true. You could impose, for example, for the action to be proper to try to solve this, but again, there are some other issues, and there are probably more things that I just can't come up on the spot. But yes, the finiteness does play a role, is what I'm trying to say. Definitely. Okay. So for the time that I have left, the idea will be basically to show that this is in fact an equivalence. And so it's an equivalence between this and all of these three categories. And that the inverse is given by some sort of cohomology theory. And so the point will be that any such functor satisfying the same conditions will be controlled by some cohomology theory, in particular the K-theory of equivariant sheaves, which will be something living here, or in any of these, will be described by some sort of sheaf cohomology. Okay, but for now we don't know this, but that's what we're after. Okay, so that's what I'm going to do next. And this is what we call a Bredon sheaf cohomology. Which succinctly put, one can define as follows. So from orbits, for example, you can include into locally compact Hausdorff spaces. In fact, we can actually make this definition for all spaces. Let me just concentrate on the locally compact Hausdorff ones for now. From this, every time you have a sheaf on locally compact Hausdorff spaces, so something satisfying open descent, you can restrict to orbits. And if you have a pre-sheaf on orbits, then you can extend to all locally compact Hausdorff spaces, and then you can formally impose open descent. You can sheafify. And this gives you an adjunction. Okay. So if we start with a pre-sheaf on orbits, then for us, Bredon sheaf cohomology with coefficients in E will just be D upper star of E. So concretely, if say we fix an X, then E determines actually a sheaf on equivariant opens of X instead of the whole category. We can just restrict. And this comes from sheafifying a concrete formula. Which is you take an equivariant, a G-invariant open in X, and then you do left-hand extension. So you map to all possible orbits, and you take E of Z. Right. So okay, this is some formula which depends on maps into orbits. This gives you a pre-sheaf on X mod G, and then you can sheafify it. And this at least gives you a formula for Bredon sheaf cohomology, which, okay, you might say it's not exactly explicit, but let me tell you which properties do we get from such a definition, and then maybe I'll speak about how to do some computations and how to obtain the main results. Right. So are we more or less okay with the definition? I know it's an abstract definition, but okay, so things that this gadget satisfies. So for example, we definitely know what it does on orbits. And this is just evaluating E at orbits. And one reason for this is that this functor on this direction is done by left-hand extending and then sheafifying. Now, we left-hand extend along an inclusion, a fully faithful inclusion. So this does not modify the values at orbits, just abstract nonsense. And then by the way we sheafify, orbits cannot be covered by anything non-trivial. So again, the sheafification process does not change the value in orbits. So at least in orbits, we know that it's just E, the functor we start with.
So, who is so the colimit runs over all the maps U to Z, where Z is
An orbit.
An orbit, and U is G invariant open. And there's a knob.
okay. Thanks.
Yeah. So it's left-hand extension along this. Actually. Okay. Right. Okay. Something else that we have is that like the very definition, there's a sheaf on this big category of all locally compact Hausdorff spaces. Something that, as far as we know, is very much not from definition is that this has cofiltered compact codescent. So in particular, it will be in one of the categories that we care about, which is functors out of LCH-G that satisfy open and cofiltered compact descent. Okay. Okay, what else? This is also G homotopy invariant. And finally, if X is a GCW, then there is a canonical comparison equivalence between this and a more classically defined Bredon cohomology of X with coefficients in E, which, to describe in few words, if you were to describe singular homology as satisfying the Eilenberg-Steenberg axioms, you might do the same for GCWs, but then instead of having to define the value at the point, you need to define the value at the orbits. Now, if you do this and then build up to have a definition for all GCWs, you would obtain Bredon cohomology. And of course, it has had several refinements along history, but that will be like a hands-on, very classical definition. And in the case our space is a GCW complex, then this theory gives you Bredon cohomology, and I hope this justifies the name. And the sheaf part is because if you have the trivial group, then you do just get sheaf cohomology. All right.
Sorry, what happens if if I have any G-space, isn't it equivalent to a GCW complex? And I don't say weak because just in case, by the same reason, I cannot say homotopic.
The quick answer is off the top of my head. Now I'm blanking. Of course, if
So,
there's no G.
there is a model structure in G-spaces so that if you take a cofivariant replacement of X, you get a GCW complex. So what I'm wondering is whether the gamma construction, what happens with the gamma construction and weak equivalencies on the space variable. Because
that should be
when we share, then this will give this statement 5 will give a description of your gamma in terms of classical Bredon, right? Classical Bredon construction. Up to replacing the space, the G-space, by the cofivariant.
Yeah, let me get back to you on that one. But even without a G, I'm not sure if you can do this generally. As in, it won't be true that sheaf cohomology, you can describe everything in terms of CWs, I think, right?
Yeah, something like that.
Yeah, I'm saying I would be wary of claiming this, but again, let me perhaps get back to you. But thanks for the question. Yeah. Okay. All right. So maybe with the time that I have left, let me perhaps first briefly say how 1 through 5 go.
Sorry, I correct myself. If what I say were true, the Farage-Jones conjecture will be trivial.
Yeah.
Because it precisely says
okay.
that, yeah. Okay, sorry.
Yeah.
The equivariant cohomology preserves weak equivalencies. That's what it says.
Yeah, that's what I'm saying. Like, I was skeptic even in the non-G case, but I think I can't think this through right now. But yeah, I would incline myself to believe it is generally quite different if your space is far from a CW. Okay. So anyway, just very quickly, the definition of Bredon sheaf cohomology tells you this is a sheaf on a locally compact Hausdorff spaces. I more or less gave you some idea of why the orbits, the value at orbits is the value of E at orbits. This I'll try to say something about in a minute. And hopefully this too. And the other thing that is somewhat formal is form. So what you can actually do is prove that if you have open and cofiltered compact descent, then you have closed descent for free. And then if you have closed and cofiltered compact descent, then you get G homotopy invariance always. So this is not a property of this functor in particular. And this for the trivial group is an argument by Hoyan that we adapted for G. So 4 is a consequence of 2 and 3. 2 and 3 tells you have open and cofiltered compact descent. So you have closed descent, and then from this, it formally will follow. By formally, I mean it won't be a property of this specific functor, but something out of all of the functors that have these properties. So basically, I just want to say some words about 3 and 5, but for the time being, I would rather first state the main theorem, which says that functors satisfying descent are equivalent to sheaves on orbits, with the inverse giving my Bredon sheaf cohomology. So on one way, if you take a sheaf, you extend it and then you restrict back. We just said that this does not modify the value in orbits. On the other hand, you could take a functor and compare it with Bredon cohomology of its restriction. But we already stated that to check that something is an equivalence, we can check at orbits. And so this reduces to a very similar argument, which is that all things have the same behavior at orbits. And so the key point is that actually this adjoint of restriction to orbits lands in this category. So point 3, that it actually has the right descent conditions. Because once we have those descent conditions, then we can check everything at orbits. And from this, it will follow that these two are inverse equivalences. Basically, you compare both compositions and both reduce to an argument of orbit-wise comparison. And so from this, since K theory of equivariant sheaves is a functor on the left-hand side, then it has to be Bredon cohomology, Bredon sheaf cohomology, of its restriction to orbits, which I'm calling KG, and which, say, point-wise looks like this. And in the same vein, if you do K theory of C cross continuous functions, then this is also Bredon sheaf cohomology NX of its restriction to orbits. And here, point-wise at least, this should be, correct me if I'm wrong, but this should be CH. Sorry. G mod H. Okay. In fact, let me just say something more about this last result, which is we can also consider.
Sorry, in the last part, you want to say cross G, right? I mean, shouldn't you have like group ring of H? Maybe I'm confused.
Yeah, most definitely. I think that was the first thing I wrote.
Yeah, I think that was the first thing you wrote.
Yeah, and then I took it back. Yeah, for sure. I mean, at least point-wise, you can identify with this, and we can speak about the functoriality, right? But yeah, and this is kind of the same that happens with the sheaves. You have sheaves on H.
Also, are you implicitly assuming things here are compact, and therefore are you working with the closed and like the compact, the CHG category? I mean, I'm
Yeah,
wondering,
sorry.
like, did you didn't distinguish between the compactly supported one and the non-compactly supported one?
Yeah, that's a good question. Sorry, I should refine the statement to this one.
Yes.
So we already know this identifies with functors on the partially defined category. And so if I call this one compactly supported Bredon cohomology, then I can do this for all X locally compact Hausdorff.
Yeah.
Again, I'm not speaking very much about the functoriality, but we do get at least for each object this identification. Right. Okay. So I have like some 5 minutes left or something, or
Yeah, 5 minutes. Wait a sec. Go up a little bit, please.
yes.
Yeah. So before you remarked this thing about the partially defined category, I mean, X, so you put the X locally compact after you did that, and then you put compactly supported. So, I mean,
Let me give it another go. So at least the way I defined it, I want to move this for a second. Where is it? Where is it? Right. So the functor is this one. And we know that, I mean, or at least I'm just telling you that this has both closed and compact cofiltered descent.
yeah.
So it identifies with things in both directions, either in LCH or LCH partially defined. So I'm just saying it corresponds to a functor here, which if one inspects it, it's still K-theory of sheaves with the functorality of lower shriek for open inclusions and upper star for proper maps. And so for that one, which will now land here, if we go back, then this has to be described as some sort of compactly supported Bredon cohomology, which as of now is just the name of the inverse composed with this equivalence. Okay. Right. Okay. Then I don't know how much I can say. Like 3 minutes. Let me just say some comments on how to prove, or the ideas that come up in the proof of 3, which is compact cofiltered codescent. So one of the main tools, or the argument, you can split in 2 parts. One, you can rephrase the argument in terms of these sheaves EX on X mod G, which is restricting Bredon sheaf cohomology to the equivariant opens of a fixed X. So you first translate what you want to prove for each X into a statement which has to do with sheaves. And then you use something about the behavior of finite groups acting on locally compact Hausdorff spaces, which is a theorem by Abels. And this basically tells you that in this specific case, if X is locally compact Hausdorff, then for each point, you have an invariant open such that U actually is induced from the stabilizer. And so from this like local description and the sheaf theoretic description of the statement we want to prove, we can prove cofiltered compact codescent. I don't think I have much time to say something about this. So let me just say one last thing, which is on this theorem, we can also consider the functor that goes into E theory before taking topology at K theory. And so we can also, maybe it's better to just say this as a remark. We can also determine the C-star algebra as an object of E theory from which we can determine its homological K theory. Okay, I think that's all I can say for now. So maybe let's just leave it to the questions. Thank you very much.
Okay, well, welcome. Thank you for a very nice talk. So, are there any questions from the audience? Well, you are met by a round of applause, as I can see. But yeah, I guess you left everybody so pleased and in awe. The only the only reaction is the applause. Okay, so I asked enough questions during the course of your talk. So I will stop the recording right now.